Welcome back, students. This is the session 11 from the playlist of moving charges and magnetism. The topic is magnetic field at the center of a current carrying coil or loop. So today we will be deriving the expression for the total magnetic field at the center of a current carrying coil or loop. So here I have considered a current carrying coil in which current I is flowing in the direction as indicated by these arrows. The radius of this current carrying coil is small r, and now let us suppose that this current carrying coil is made up of a large number of very small current carrying element, say dl. Now dl is what? Basically it is the length of a very small current carrying element, and a large number of these current carrying element make up the total length, or you can say the circumference of this loop. So here I have taken the length of this very small current carrying element as dl, and here this loop is made up of a large number of these small current carrying elements. So according to the Biot-Savart law, the magnetic field at this point, that is the center of this loop, due to this very small current carrying element, will be equal to mu naught upon 4 pi I dl sine theta upon r square. Now this is basically the Biot-Savart law, and this is the formula which all of you must be knowing about it. So this is the formula as given by this law, and here theta is the angle between the current carrying element and the line joining this element to this point O, that is the center of this current carrying loop. So here this angle is equal to theta. In this case, theta is equal to 90 degree. So from this equation, I am getting the magnitude of the magnetic field due to this very small current carrying element of length dl as dv is equal to mu naught upon 4 pi I dl upon r square into sine of sine theta. Since theta is equal to 90 degree, so sine theta will be equal to 1. Now if I integrate this equation, I will be able to get the total magnetic field at this point, at the center of this current carrying coil, due to all the small current carrying elements dl. So by integrating this equation, I am getting the value of magnetic field B as mu naught upon, now mu naught upon 4 pi is a constant, I is also a constant, r square is also a constant, so that can be taken out, and this is equal to integration of dl. Now integration of dl will be equal to what? This will be equal to the integration of dl. Basically it is what integration of dl means. It is basically the sum of the length of all the very small current carrying elements dl, which is making up this current carrying loop. So this will be equal to, basically it will be equal to the circumference of this current carrying loop, and this will be equal to 2 pi r. So I will be now substituting this value in this equation, and I will be able to get the value of the magnetic field at the center of this current carrying coil and this will be equal to, this R and R will get cancelled out, this pi and pi will get cancelled out, and this 2 into 2 is equal to 4, so this is equal to mu naught I divided by 2R. So the total magnetic field, or you can say the magnetic field at the center of a current carrying loop is equal to mu naught I upon 2R. So in this session I just wanted to derive the value of the magnetic field at the center of a current carrying coil or the loop, because these type of questions are sometimes even asked in the board examination. So this question or this derivation is important from the point of view of the board exam preparation. So thank you very much for joining this session. In the next session I will be taking up another topic, and that will be the Ampere's circuital law. So till then, have a nice day. Bye.